When we think of fusion energy, most of us get this picture in our heads of a giant metal donut. But what if the key to unlocking fusion power isn't a donut at all? What if it's a completely different shape? Well, today, we're diving into the world of alternative fusion designs and the one critical number that really sets them all apart: plasma beta.
There's this great line people often say it came from the physicist Robert Bussard, and it's a classic jab at that mainstream tokamak design. Now, obviously, he's not being literal, but it makes a really deep point about the fundamental physics of trying to contain a star in a box.
And that's because the shape, the actual geometry of a fusion device, dictates pretty much everything. I mean, it determines how well it holds onto heat, how stable it is, and even how ridiculously hard it is to build and maintain. The thing is, none of the designs get a free pass here. They all just pay different costs in different ways.
So to really understand these different costs and benefits, we've got to get familiar with one key metric. It's a number you're going to hear thrown around all the time in this field, and its name is beta.
So what is it? Put simply, beta just tells you who's winning the pushing match inside the reactor. Is it the magnetic field trying to squeeze the plasma, or is it the super hot plasma pushing back? If beta is low, well, the magnetic field is in total control. But if beta is high, the plasma is putting up a serious fight.
Now, this is where a lot of people get tripped up. A high beta, even one that gets close to that magic number of 1, doesn't mean the magnetic cage just vanishes. Nope. Instead, the plasma's own pressure becomes so strong that it actually starts to warp and reshape the magnetic field from the inside out. And that is an incredibly powerful effect.
And getting to this state, this place where the plasma pressure and the magnetic pressure are basically in balance, that is the central goal for a whole class of fusion concepts that, you guessed it, look absolutely nothing like a donut.
All right, so let's meet some of these contenders, shall we? These are the machines that are specifically engineered to thrive in this high beta environment, where the plasma itself is helping to do the hard work of confinement.
So on one side, you have the low beta tokamak, our friend the donut, which has to rely on this massive external magnetic field running the long way around the torus. But on the other side, you have something like the field reverse configuration, or FRC. It's a compact cylinder, it operates at high beta, and it has a totally different magnetic structure. And here's the kicker. High beta means it needs a less powerful and therefore cheaper external magnet system to get the same amount of fusion power. That's a huge deal.
And the FRC isn't the only one in this high beta family. You also have concepts like the polywell. This thing uses a really unique cage of magnets to create these things called cusps that trap electrons. The whole goal is to build up a powerful electric field that then traps the fuel ions. And again, high beta is absolutely essential because it helps to plug the leaks in this magnetic cage.
So, how in the world do you actually get to these high beta states and, keep them there? Well, it turns out a key piece of technology they use isn't just a heater, it's more like the ultimate multi-tool.
We're talking about something called neutral beam injection, or NBI for short. In FRCs, these incredibly powerful particle beams do 3 crucial jobs. First, of course, they heat the plasma up to fusion temperatures. But second, they sustain it, constantly refueling it with energy and particles. And third, and this is maybe the most critical part, they act like a control knob, helping to stabilize the entire plasma configuration. It's just an incredibly versatile piece of tech.
Okay, let's switch gears for a second, because you might be hearing about high beta fusion in the news lately for reasons that have a lot more to do with Wall Street than with a physics lab. And it's really, really important that we separate the financial headlines from the actual physics.
So here's the headline. Recently, Trump Media announced a major merger agreement with TAE Technologies, which just so happens to be one of the leading companies developing a high beta FRC. And as you can imagine, this has brought a whole lot of new attention to the field. But this is the crucial point, and our source material says it perfectly. This is a business event. It tells you something about market confidence, about corporate strategy, but it does not, by itself, prove that the underlying science works. And to be fair, it doesn't prove that it doesn't work either. It's just a different conversation. And here's how that business strategy can make a lot of sense. You see, companies like TAE are developing these amazing enabling technologies, like those neutral beams we were just talking about. Well, those beams have immediate uses in things like medicine for cancer therapy or in semiconductor manufacturing. They can actually sell this tech today and generate revenue long before they ever build a power plant. It's a clever path. All right, so with all this news, all these different concepts flying around, it can feel, frankly, a little overwhelming. How are you supposed to sort the real hype from the real progress? We're going to finish up with a practical checklist to help you do just that.
So the next time you hear about some new breakthrough or a secret sauce that's supposedly going to solve fusion once and for all, what are the tough questions you should actually be asking?
Here they are. It's not about one single magic number. It's about the entire picture. How good is the machine at holding on to energy? How do they handle impurities that can poison the reaction? Does the power budget actually add up? Are they putting more power in than they're ever going to get out? How efficient are the tools they're using, like those neutral beams? And critically, are the materials and the engineering even plausible for a real-world power plant? See, real progress shows up as solid, credible numbers across this entire list.
So at the end of the day, the key takeaway is this. High beta is an incredibly promising path. It's a powerful engineering tool that could lead to smaller, maybe more efficient fusion reactors. But it is not a magic shortcut. It doesn't just erase the fundamental challenges of confinement and stability and power balance. So the next time you see that big headline about a fusion breakthrough, doesn't matter if it's about a donut or a cylinder or something else entirely. I hope this gives you the tools to look past the rhetoric of some secret sauce and to start asking the really important questions about the numbers.